This video is on LeChatelier's principle. Now, LeChatelier's principle is when a stress is applied to a system in equilibrium, the system will react in a way to relieve the stress. So you can kind of think of these systems or these chemical reactions as a teeter-totter. And if I increase or decrease the weight on one side of my teeter-totter, it's going to shift appropriately to compensate for that weight. Okay? That's all that these chemical reactions are doing. They're compensating for what you're doing to it. That way they go back to their equilibrium state. There are a couple different stressors that we can implement on our chemical reaction. The first of which is adding a chemical. Your reaction is going to shift away from that addition of the chemical to shy away from it. That way it decreases how much you added. Next, if we remove a chemical, that's like creating a hole in your reaction, and your equation or your equilibrium is going to shift towards where the chemical was removed to replace the chemical that you removed. If I increase the temperature, I'm going to increase the amount of energy in my system. And as I increase that, again, my system's going to shift away from the increase in temperature. If I decrease my temperature, my system is going to shift toward my temperature, going to make up the energy that was lost by decreasing the temperature. If I increase my pressure, this deals only with gases. If I increase my pressure, my equilibrium is going to shift towards the side of reaction with less moles of gas. Therefore, there's going to be less interactions there. It'll be a happier state. If I decrease my pressure, my equilibrium is going to shift towards the side with more moles of gas because there is now more areas for it to move around. And then if I add a catalyst, this actually does not change which direction my equilibrium is shifted because catalysts only speed up or slow down the reaction in the sense that it decreases the activation energy. It doesn't increase or decrease how much you have. So standard format is to have reactants on the left-hand side of your equation, products on the right-hand side of our double arrow there. So if my equilibrium shifts to the right, that's going to shift my reaction toward the products. I'm going to increase my amount of products, decrease my amount of reactants. If my system shifts to the left, I'm going to decrease my amount of products, increase my amount of reactants. So let's go through an example. The example is of the Haber process, a process that you will learn about. Either you have learned about it by watching the video or you will be shortly. This is also the same process that is talked about in Pogel number 3. You have nitrogen plus hydrogen, both gases, in equilibrium with ammonia, which in this case here will actually give off heat. Now, if I add H2 to my system, I want to know which direction it shifts. From that shift, is that going to increase or decrease my products? Increase or decrease my reactants? As I add H2, it's increasing my amount here. Because now I've increased my amount here, my reaction is going to shift to the right to use up my added H2. Therefore, it's going to increase my amount of products and decrease the amount of reactants I have to minimize everything back out, allow it to go back to its equilibrium state. If I remove N2, so I take away my N2, that creates a hole here. My equilibrium will shift to the left to fill in the hole, which will decrease the amount of products I have and increase my amount of reactants. Now if I increase the temperature here, you'll notice that my reaction gave off heat. That's like having a positive delta H or a positive energy associated with it. If I increase my temperature, I'm increasing my amount of energy or heat, which is then going to push my reaction towards the left, decreasing my products, increasing my reactants. If I increase the pressure of my system, my reaction wants to shift to the side with less moles of gas. Now I have 1 plus 3 moles of gas here, so a total of 4 moles of gas in my reactants. I have 2 moles of gas in my products. Now I want to shift with a high pressure. I want to shift to the side with less moles. That's going to go this way. Since there will then be less things bouncing into each other, less moles bouncing around. And therefore I'm going to increase my products and decrease my reactants. Finally, if I add a catalyst, that actually does not change my equilibrium. that just allows my reaction to proceed with the lower activation energy. So therefore it does not increase or decrease my products or reactants. If this was just a forward reaction, that would decrease my activation energy, and a reverse reaction would also decrease my activation energy, but that will not have a hindrance on how much product or reactants we have.